Well, welcome to the last day of classes. Here's a few reminders. We'll have a math club today at 5 o'clock here. Like I said, I think this might be of interest to some of you because what we have is we have people that have done internships, telling you about their internships. And I know especially you engineer folks, you might have that kind of thing on your radar for the future. The math end tomorrow, 10 a.m. to 5 p.m. in this building, one of these rooms. It will be clear when you get here. Take advantage of this. Show up with your friends. We'll have a linear algebra party. Get ready for the final kind of thing, or any other classes that you're in. We will have a second review from this class, 5:45 p.m. Thursday, a week from yesterday, right here. Don't forget to do your assessment. You've got to come see me before the final exam, if you want to do that. And also, don't forget to do the class evaluations. They have to be done by close of business. Everybody does it, you'll get an extra, everybody gets an extra 100. Also, office hours. Let's see, you guys got Monday, Wednesday, we'll say 8. I'll make myself available Monday and Wednesday at finals week, like next week, Monday and Wednesday. So it'll just be like a regular day, except for it won't be at 7. And also, I don't teach classes during finals week, so you got a couple extra in there. Friday, we'll say. Whenever I have to leave to come up with the file, I can come in earlier if you like, so just let me know. Also, I'll be around Tuesday and Thursday as well, but you're taking your chances because I've got other things going on. So, you know, but if you catch me in a free moment, I'm perfectly fine with that. Okay. Any questions about any of this stuff? Y'all have actually been a pretty good class, so let's finish strong. Questions? Ooh, I bet Sam has a question. Which one was it?
It was the last question on the most recent quiz that we submitted, so not the one that's like currently out.
That would be quiz 24 probably. Well, I'll know it quickly enough. It's all the integral stuff, right? So how many of you all had to contact your therapist when you saw that there was all these integrals on there, right? I mean, that kind of, so let's do this. So what we have here, by the way, this is question 2 from quiz 24. We consider the vector space of all functions that are continuous from minus power 4 to power 4, equipped with the inner product. And I've got an inner product, and I don't think I expected you to show this an inner product, but in fact, because we talked about continuous functions in general, I think this is an example we did in class where I talked about why this was an inner product, right? And one of the things that depended on delta epsilon stuff. The inner product f of x and g of x is equal to the integral from minus power 4, product. So this is, like I said, this is something we saw in class, and now we're applying it to a particular situation. First question was find the length of the functions sine x, cosine x, and tangent x. Yep. So how do we use an inner product to get a length? When we have an inner product, how can we use that inner product to get a length? Take an inner product from itself, right? And that'll give you the square of the length. So at the end of the day, you'll have to take square root of it, right? Well, let's just go ahead and find this. Right. And of course, you're integrating a positive function in the positive direction, so this has got to be a non-zero number, so that's good. Anybody remember in the old days how you integrate sin x? I mean, if this was just been the integral sin x, that would be easier, right? Sin squared x is problematic. Anybody remember how to do it? Well, the first thing you should do in a situation like this is look further down the quiz to the crap I wrote in red, with some trig identities, and sin squared x turns out to be. Does that ring a bell from the old days, perhaps? Or maybe not. I mean, you all have integrated trig functions before at some point in the past, right? So this is. And this is, of course, much easier to integrate. What can anybody tell me what the antiderivative of cosine 2x is?
2
Right, it's just sine 2x over 2, right? Because this, I mean, you could do a u substitution, but it comes out to be -1/4 sine 2x. And by the way, it's easy to check this, isn't it? Right, because if I take the derivative of this, then I should get back to this, and I get 1/2, and then I get 1/2 cosine 2x. All right, so readily checkable. From. And by the way, I'm gonna record this information as I get it over here. So this is pi over 8. When I put in power 4. This is going to be sine of pi over 2, which is 1. Minus, when I plug in minus power 4, I get minus pi over 8. And when I plug in minus, so then we get sine of minus power 2, which is -1, so it's +1/4. And so that's 2/8 pi minus 1/2. And that's a little bit bigger than 3/4 pi, that's positive, so that's good. So this is something like pi minus 2. Now, I'm not quite done yet because I want the length of it. And there we go. So I'm gonna kind of record this information as I get it over here. Because it's going to be useful later, perhaps. Okay, so far. The length of cosine x. Let's go kind of through the same process. Well, first let's find the inner product. And you use the same trick, that is, you use that identity that I've got down there. And this is. And this is now going to be 1/2 plus 1/2 cosine 2x. dx. Which equals 1/2 x plus 1/4 sine of 2x. Of course, evaluated from power 4 minus power 4 to power 4. Okay. All right, so we plug in. Power over 8. And then that's going to be sine of power 2, which is 1, so it's going to be another 1/4. Minus, when I plug in minus power 4, I get minus power over 8. And here I'm going to get minus power over 2, so it's going to be -1/4. So this time I get 5 over 4 plus 1/2, which is pi plus 2 over 4. With the length of cosine, Be the square root of that. Okay. So for this particular inner product space, looks like cosine's a little bit bigger than sine. Okay, finally, let's look at tangent. I think this one's actually a little bit easier. Let's see. Anybody know how to do tangent squared of X? How about a trig idea relate tangent squared to something else? Okay, good. This is, somewhere in my past, I seem to recall that the tangent squared is minus one. Now, why is it easier, right? I've turned tangent squared basically into a secant squared, but this is easier. Anybody know what the secant is? Do you think a function is derivative of secant squared? Easier. Just plain old tangent. So the antiderivative of this is tangent x minus x. Derivative of tangent of secant squared, derivative of x is 1. So plug in pi over 4, I get 1 minus pi over 4 minus, when I put in negative pi over 4, this is minus 1 plus pi over 4. So at the end of the day, it looks like I get 2 minus pi over 2, which is 4 minus pi over 2. You like? So the length of tangent x should be the square root of this. Well, so there's the 3 lengths we had. Then I asked this kind of cryptic question in the middle because it's actually kind of designed to help you out. Of the functions sine x, cosine x, tangent x, one is orthogonal to the other 2, and 2 of them are not orthogonal to each other. Which is the function that is orthogonal to the other 2? Okay. Okay, I get the new integrals again. Or do I? So I have got these 3 functions here. Which one is orthogonal to the other 2? Let me remind you. I guess I could go through and compute every one of these, right? And see, what does it mean to be orthogonal? I should do some crazy interval and get 0, right? But there's a simpler way to think about this. You might see it a quick way. In fact, I'm gonna tell you what the answer is. I can tell you without writing anything down that cosine is orthogonal to the other 2. How do I know that? Without writing anything down. Yeah,
Because cosine is an even function.
that is exactly right. And the other two are, is. Agreed. So what happens in your inner product? You get the product of these two and you integrate it on a symmetric interval. Minus power of 4 to plus power of 4, right? This interval that you integrated on is symmetric. And so when you integrate an even function, I didn't draw very well, if you integrate an even function, it doubles the interval from 0 to 2. What happens if you integrate an odd function? What happens when I integrate that from negative power 4 to power 4? What do I get? It's 0. Right? Notice that sine x, cosine x, odd, and tangent x, cosine x, is odd. So cosine x is orthogonal to sine x and tangent x. Go ahead and work the intervals, but don't. Right. Everybody see why that's true? That's the quickest, slickest way to do that. It's just, look, these two are odd. They have to be the two that are orthogonal to the middle one. Okay. Right. Find an orthogonal, actually, and you all should thank me profusely, because when I first wrote this quiz, when I first wrote this quiz, I had functions that were much worse than this, and I also wrote an orthonormal basis. That would have been awful. So I backed it off to orthogonal. This will help with this, right? In fact, you only have to do one thing here. If you started right, find an orthogonal basis to the space spanned by let's build this. This is part C. There we go. I'm 2/3 done. Right, just do this. Right, it's and actually, yeah. I'm 2/3 done already, right? Because sine x, when you're building an orthogonal basis, you could just start with the first vector, in this case sine x, make your second vector cosine x, and you already know those two are orthogonal by the previous part. So the only thing you got to do now is to figure out how tangent fits into this mess. And it is a bit of a mess, but we will overcome. So the final element so let's Gram-Schmidt the crap out of this thing to get the final element. How do we do this? Well, our new element is tangent x minus the inner product of sine x tangent x over sine x sine x minus inner product is with cosine there's your answer. Now all I got to do is figure out what the numbers are. Right? First of all, does everybody follow my application of Gram-Schmidt here? Is everybody cool with that? Okay, second, somebody shortcut this, right? It looks like I have to do a bunch of inner products, but it's really not. Yes, sir.
You can drop off the last term because the inner product's zero.
Right, and once again, from part B, this inner product is zero, so this, come on, it's Casper, it's a ghost. Here we go. This piece is zero by part B. So this chunk is gone. So all I gotta do to figure this out is get this. And guess what? I know what this is. I've already done this. I mean, we got the length, but all we gotta do is square this thing and we've got it. Everybody agree with it? So the only thing that we have left to do is integrate sine x times tangent x. That's it. Right? So let's do sine x tangent x. And this one's a little bit obnoxious, but it's not obscene. This is going to be sine x tangent x dx minus over 4 over 4. So what should we do here? How many of you consider yourself trigonometric prestidigitator? Right? Sometimes the trig functions confuse me a little bit too. So you know what I do? I do just what REM did on their monster album. I go back to my roots, right? And this is the integral of sine squared x over cosine x. Back to my roots means that I just rewrite none of this fancy stuff. It's all in terms of sines and cosines. You can do that for any trig function, all in terms of sines and cosines. Yeah, I'd love for it to be u equals the bottom, but that doesn't work because I've got a road power of sine on top. How do I get through this? Okay. Anybody know the trig identity for sine squared? Nothing too fancy. In fact, maybe basic. Yes.
1/2. Oh, sorry.
Well, in fact, I'm gonna let him go with that because that's a fancier one. How about a simple one?
1 minus cosine squared.
Let's do that one. Let's do 1 minus cosine squared. Your identity was correct, but I'm not sure it would help me see what's going on here. So this comes to. Great. Write this down. That's what it is. And now I think I've put this into about as simple as I can. Everybody here remember what the antiderivative cosine is? That's cool. Secant's a little bit more tricky, but fortunately for you, it's in red. Quiz. This is the natural log, absolute value, secant x plus tangent x minus sine x. See if we can do this. This is log, see when I'm putting the total 4, that's radical 2 plus 1. One of my favorite numbers. Minus sine of power 4 is 1 over radical 2. Minus, put a minus power 4, I get minus let's see, cosinus go. Yeah, radical 2 minus 1. Oh, log there. And sine of minus power 4, so it's going to be plus. Okay. So this comes to log radical 2 plus 1 minus log radical 2 plus 1 or minus 1 minus radical 2. Just to make the formula more compact, you don't have to really do this. But I also wanted to kind of convince myself that this is positive, right? Because remember what this is, well, no, it doesn't have to be plus, not bad. Yeah, because I'm doing that in a product scheme thing. I made this more compact. This is log radical 2 plus 1 over radical 2 minus 1. That's radical 2. And this is log. Simplifying. I don't care too much about it. So here's the last piece of the puzzle. This last basis element should be tangent x minus inner product of sine x tangent x over sine x and sine x. And then the inner product of cosine x and tangent x, which converts it to 0. So this is equal to tangent x minus the inner product of sine x with itself is pi minus 2 over 4. And this one we just figured out is this crazy thing. Natural log 3 plus 2 radical 2. So if you wanted the last basis element here, which you need to be orthogonal set, if I clean this up a little bit, it's tangent x minus there's the last basis element. Somebody explained to me why I did you a favor by not asking for an orthonormal basis. Nobody wants that, right? These two would have been easy enough because I've already done it, right? But this thing, you have to integrate this and then integrate this with a constant in front of it, and it would just be another constant, but it would be just a mess. Okay, any questions on that? So maybe you haven't done integrals in a while, but does this look familiar to everybody? The stuff I did? Okay, good. Other questions? Yes.
You did number 1 on this.
Number 1 on 23, sure. Well, we'll see. That's close. Okay, so I give you a set of vectors here. Put this down. So there's a set of vectors here, B, and I call them B1, B2, and B3. And I've got 1 over 1. I've got 3, 2, I've got 2. Okay, it says use Gram-Schmidt to find an orthogonal basis for the span of this. So A, use Gram-Schmidt to find, let's see, orthogonal basis. For the span of this. By the way, it is of course possible to get different looking orthogonal bases depending on which one you start with, right? In fact, we've seen that, for example, even for R2, E1 and E2 is an orthogonal basis, but so is the vector 1, 1 and 1 minus 1, so orthogonal as well. But I'll go through it. I'll start here. I'm gonna let me call it basis B1 is equal to 1, 1, 0, 1. So I'm going to just use this C to start. All right. B2 is the second vector adjusted minus B1 dotted with B2, B1 dotted with B1 times B1. With 1, 1, 0, 1. Everybody okay with that so far? Okay, so we get out this. This is 3, 0, 1, 0 minus, let's see, B1 dotted with B2 looks like it's a 3. Everybody agree? And B1 dotted with itself also looks like a 3. So this is 1, 1, 0, 1. So it basically it's this minus this. So I get 2 minus 1, 1 minus 1. I think. Minus 1, 1. Everybody agree with that? This is what I would call my B2. And finally, my B3 should be 2, 1, 2 minus B1 dotted with B1 and B2 B3 B2 dot B2 and whatever B2 was 2 minus 1 1. Oh, by the way, what's a gut check that I just now did in my head? I probably should have done it anyway. What's a good kind of gut check when I get here? You should probably make sure it's orthogonal as the original, right? So in the second step, we got 2 minus 1 1 minus 1. But if you check the dot product with 1 1 0 1, it'd be 2 minus 1 is 1 minus, so it's orthogonal. So that's good. At least I know I'm on the right track. Let's see what we get here. This is 2 1 2 0. Okay, let's see. I need B1 dot B3. And what's that going to be? B1 dot B3 is, looks like it's 3 to me. B1 dot itself, I did in the last problem, is 3. 1, 0, 1. And we'll see B2 dotted with B3. What's that going to be? It's like it's 5, doesn't it? Do I agree with that? B2 dotted with B3 looks like it's going to be 6, 5. And I need B2 dotted with itself, which is going to be 4, 5, 6, 7. Looks like it's going to be 7. Two. What am I doing? It's 2 minus 1, 1 minus 1. Way I feel that. This one I'm going to do a little bit more computation. So this is, let's see, this is just subtracting 1 from it. So I get 1 0 2 minus 1. this minus is, 2 minus 1 is 1, 1 minus 1 is 0, 2 minus 0 is 2, 0 minus 1 is 1. And what do I get in this? This is going to be minus 10 sevenths. This is going to be 5 sevenths. This is going to be minus 5 sevenths. And this is going to be plus 5 sevenths. So the last vector I get in computing this orthogonal basis, and I should probably tell it here, is, well, minus 3 sevenths, 5 sevenths. That's going to be 9 sevenths. And minus 2 sevenths. Now I should probably gut check this. Let me write down what I've got here. What do I have? I have 1, 1, 0, 1. The next vector was 2 minus 1, 1 minus 1. And the last vector, I don't want to write all those stupid sevens in there. So I'm going to rescale this to minus 3, 5, 9. Minus 2. Does everybody see how I scaled it? Right, this just makes it easier for me to check. Now, for this to be an orthogonal basis, all they have to do, I already know these two have dot product 0. What happens when I dot these two? I get minus 3 plus 5 is 2, minus 2 is 0. When I dot these two, I get minus 6, minus 5 is minus 11, plus 9 is minus 2, plus 2. Okay, good. I think this works. Everybody okay with it? So that's good. Once again, we have to check ourselves. So that should be an orthogonal basis. It's not the unique one. It says find the QR factorization for the matrix, the 4x3 matrix with column can be. Okay, so we need a QR factorization. There it is. Or the matrix that has these columns here. So that would be 1, 1, 0, 1, 3, 0, 1, and 2, 1, 2. And I'll call this A. Yeah, do this. Anybody remember? So what is Q? Or how do we form it? And what should R look like? You can do QR factorization when you have linearly independent columns. And I know these are linearly independent columns because I just performed the Gram-Schmidt process on it. And it was right, I got an orthogonal basis, right? So what you do is you take the columns here and you replace them with an orthogonal basis for the column space. So Q, I've got one almost ready made. I can almost use these for columns, but not quite. What do I have to do? Orthogonal. I have to make them, they're orthogonal. I have to go the extra step and make sure that they all have length 1. For this one, what do I have to divide out by? Radical 3. Agreed. So for this one, what do I got to divide out by? Radical 7. Agreed. Radical 7. Actually, I'm gonna have to spread you out there. Minus 1 over radical 7. 1 over radical 7. 1 over radical 7. The last one. radical what, 117? Let's see, 4 and 85, 25. 10, 190. Yes, you got it in 9. I guess it's bracket 119. Yeah. 34, 81. 115. Yeah. So this is -3 over radical 119. 5 over radical 119. 9 over radical 119. And -2 over radical 119. All right, well, if I remember QR right, there we go. I've got that. But how do I get the R? And by the way, what's the R supposed to look like? You might remember? Remember what it's supposed to look like? This is actually helpful in knowing that you're getting a reasonable answer or not.
It's A times the transpose.
Oh, that's how you find it. Yeah, yeah. So, you have, the goal is A is QR, right? So that means that R, well, let me write it this way. That means that Q transpose A should be R. And actually, maybe when we do this computation, you'll see, be reminded what this is. So let's figure out what R is. R should be just Q transpose times A, which in this case is right, and
Oh, it's
9. And times A, the original A, which is easier, 1101, 2, or I'm sorry, 3010, and 2120. This should be what, a 3x3 matrix, right? Because it's 3x4 times 4x3. And I get, let's see, 1 over radical 3, 1 over radical 3, radical 3, that's 3 over radical 3, which is radical 3. Second column, I get 3 over radical 3, 0, 0, 0. 3 over radical 3 is radical 3 again. Finally, 2 over radical 3, up to 3 over radical 3, 0. Looks like radical 3 again. Right, okay, so let's look at the second one. 2 over radical 7, down to 1 over radical 7, down to 0 over radical 7, so I get 0 here. This is going to be 6 over radical 7, up to 7 over radical 7, 0, so I get radical 7. Let's see, 4 over radical 7, down to 3 over radical 7, up to 5 over radical 7. And that's what we say down to see 2, 4. There. And finally, the last row, all over radical 119, I get -3 plus 5 is 2, minus 2 is 0. This times this, over radical 119, I get -9 plus 9 is 0. And finally, I'm going to have -6 over radical 119 plus 5. Going up to -1 over radical 19. So 18 is, I guess, 17 over radical 119. Double check that. 18. and this is your R. So go back and check, multiply Q by R, and you should get the original A. Does anybody remember now what form R is supposed to take?
Upper triangle.
Upper triangular, there's one more thing. Positive entries on the diagram. Good. Okay. Victor, is that solved for you? Okay, others. Any other? Yes,
Question 5 from the 2022 final.
yeah. Okay, question 5 says. Okay, this is a singular value decomposition theorem. So let me kind of go through this fast. You can ask me again if I don't cover enough details. Oh, and when time runs out, you can certainly leave in case I run over. But let me go through this, and if this doesn't stick, we can just come back and see me. So basically, the goal of this is to do one of these singular value decomposition deals. And since it's on the final, it's probably not too very grueling, I hope. Okay, so you're given this matrix. It says find the matrices sigma and VT in the singular value decomposition. So if I'm going to do a singular value decomposition, what's the first thing that I have to do?
Find the eigenvalues.
Right, but of course this matrix no eigenvalue. So what do I have to do to get me to a matrix where I can find eigenvalues? So I got to do that first. And A transpose is 304, and A is 304. And so this should be a 3 by 3 matrix. It should be 9,012, 0, 0, 0, 12, 16. Everybody agree with that? By the way, I promise you that one of the eigenvalues has to be 0. Right, because the determinant of that is clearly 0. You got a row of zeros. One of the eigenvalues has to be 0. So let's find the eigenvalue. 9 minus x, 0, 12, 0 minus x, 0, 12, 0, 16 minus x. Hopefully this won't be too bad. I get 9 minus x times this determinant here, which is just x squared minus minus 16. Okay. I get 0 here, and then I get plus 12 times this. It's going to be 0 and plus 12x. That means 16x. 16x, right? Is that what you're correcting me on? Is that better now? Okay. So let's see what we get. Notice I can make this a little easier. There's a factor of x here and here. So this is x times 9 minus x times x minus 16 plus 144. So what do I get? This is x times this bit right here is going to be minus x squared. That's going to be plus 25x minus 144 plus 144. 144 is canceled. And this is x times minus x squared plus 25x. Which is minus x squared, x minus 25. So my eigenvalues 45 is 0. All right, so to find So I've got the singular value. Are those, right? So, I can already do this. I know it has to be a 1 by 3 matrix. There's that, it's just a singular value. The non-zero singular value. To find V, what I need to do is I need to find a basis orthogonal eigenvectors. So for lambda equals 0, I get the matrix 9, 0, 12, which I will simplify by dividing out by 3, and 12, 16, I'll simplify that by dividing out by 4. So I get the eigenvector minus 4, 0, 3. And for lambda equals, actually I should get, that's only one of them. I'm being sloppy here. There's actually 2 free variables here. So what I get is I get 3x1 plus 4x3 equals 0. Or x1 plus 4/3 is 3, 0. So my eigenvector looks like this: x3, x2, and I get minus 4/3. So I get 2 eigenvectors, and it minus 4, 0, 3, and 0, 1, 0. I get lucky with these eigenvectors. Can somebody tell me why? What's lucky about these? They're all already orthogonal, right? If they weren't orthogonal, I would have had to Gram-Schmidt it to get it down there. For lambda equals 25, I get the matrix 9 or minus 16, 0, 12. I know. And 660. It's 9. 16 minus. And here, and I get minus okay. Now this one, these again 2 are the same. So this is 1, 0 minus 3/4. And this 0, 1, 0, and this is 0. So I get one linearly independent eigenvector here. And that is eigenvector 1, 0, and so I can do it this way. Yeah, only it's plus. There we go, and that should be perpendicular to the others, and it is. So my V should be. Let's do this in the order of the values, right? Notice this was the positive one. This came from the eigenvalue 25 with the singular value here. This is 3/5, 0, 4/5, and the order here doesn't matter. Minus 4/5, 0, 3/5, and 0, 1, 0. And there's your V. Because now you've got this corresponds to the eigenvalue or the singular value 5, the eigenvalue 25. And these other 2 are from the or an orthonormal basis for the eigenspace 1. And finally, how would you find the U? remember this, UI equals 1 over sigma I VI. And by the way, what should the size of U be? What should the size of them? So at the end of the day, we have A, which is 304. And this should be U sigma V transpose. And I already know what sigma is. It was 5, 0, 0. And V transpose is the transpose of this thing, which is 3/5, 0, 4/5. Minus 4/5, 0, 3/5, and 0, 1, 0. What's the size of this matrix here? Well, so remember, this has to come out to be a 3 by 3. When you multiply this here, this is what, this is, or I'm sorry, 1 by, it's a 3 by 3. What size does you have to make it come out? 1 by 1, you gotta love that. So there's only one, there's only U1, which would be 1 over this, because the singular value is 5, times, it's not V1, only V1. So your V1 here, the matrix here, A was 3, 0, 4, and V1 is 3/5, 0, 4/5. Now let's pray for this to all come out. This is going to be 9/5 plus 16/5, which is 25/5, which is 5. So U1, all that trouble just to get a 1, right? But that should be the decon, replace U by 1, and there's your single value.
So where did you get sigma equals? Okay,
Sigma equals.
like,
Oh, this one right here.
yeah,
Remember, these are the singular values, and they are the square root of the eigenvalues in decreasing order. My eigenvalues are 25 and 0.
right.
So singular values are 5 and 0. Yes, sir.
With the matrix V, why did you divide it out by 5?
I wanted to make it, when I'm building V, it needs to be orthonormal. Yeah. All right, I'm enjoyed having y'all. Sorry to run over, but hopefully that example is helpful, and hopefully I'll see y'all in the back end. And we'll get the insight.